Welcome everyone to this explainer. I am absolutely thrilled to have you here today as we dive into Chapter 1, Introduction to Computer System. If you've ever held your phone or looked at your laptop and wondered how a simple piece of glass, metal, and silicon actually, thinks, you are in the exact right place. Today we're totally decoding the blueprint of modern computing. We're going to break down the anatomy of a computer system, going all the way from its physical, tangible body right down to its invisible working mind.
So here's our roadmap for the explainer. We'll start by officially meeting the computer system. Then we'll crack it open and step inside the processing unit. After that, we'll cover computer memory and data, trace the evolution of computing, and finally, we'll wrap up by looking at why hardware absolutely needs software.
But before we get completely lost in the wires and microchips, let's start with a little philosophy. The legendary Alan Turing once said, "A computer would deserve to be called intelligent if it could deceive a human into believing that it was human." I just love starting with this because it frames the ultimate big-picture goal of computing. We aren't just building fancy calculators here, we are literally attempting to build intelligence. But to reach that kind of ultimate goal, we first have to really understand the mechanical reality of how these machines actually function.
Okay, let's jump right into Part 1. Meet the computer system, the anatomy of our digital tools. So what exactly is a computer? Cut through all the jargon, and at its core, a computer system is just an electronic device programmed to do three fundamental things. It accepts data, processes that data, and generates a result. Honestly, it's a lot like the basic metabolic cycle of a living machine. You feed it raw materials, that's your input. It digests and transforms that material, that's the processing, and then it spits out something useful for you, the output. And the whole shebang happens through a totally seamless partnership between hardware and software. So where does all that crucial processing actually happen? Let's move into our next chapter, inside the processing unit, the brain of the machine. The famous von Neumann architecture brilliantly illustrates exactly how this brain sits within the wider system. It's all about the flow. Data travels from your input devices directly into the central processing unit and the primary memory. The CPU crunches the numbers, stores those results back in the memory, and eventually pushes that processed data out to your output devices. It's a closed, perfectly logical loop. Now let's zoom in a bit closer on that CPU, or microprocessor. It's definitely not just a single mysterious black box. It's made up of very specific functional areas. You've got the ALU, the arithmetic logic unit. This is basically the calculator doing all the heavy lifting, the actual math and logic. Then you have the CU, the control unit. Think of this as a traffic cop, directing the sequence of instructions so nothing crashes into each other. And finally, you have registers. These are tiny, lightning-fast pockets of local memory situated right on the CPU chip. They act as the processor's immediate scratch pad while it's actively working on a problem.
Hey, a brain is completely useless without a way to interact with the world, right? That is exactly where inputs and outputs come in. Just like you and I need senses to perceive things and mouths to speak, a computer relies on input devices, like a keyboard or a mouse, to capture your signals in a digital form. And then it uses output devices like monitors, printers, or speakers to translate its digital thoughts back into a form that we humans can actually understand.
Now, keeping with the brain analogy, a processor desperately needs a place to keep its information. Let's turn the page to computer memory and data, how a computer remembers.
There is a really profound difference between the two main types of primary memory. First, we have RAM, or random access memory. This is your computer's short-term memory. It holds the data you're actively working on right now. But the catch? It's volatile. That means the absolute second you turn off the power, poof, it clears out, just like falling into a deep sleep and forgetting what you were just thinking about. Then we have ROM, or read-only memory. This stuff is non-volatile. It holds permanent, unchanging instructions like the ones required just to start the computer up in the first place. If RAM is short-term memory, ROM is basically our deeply ingrained human instincts.
And how on earth do we measure all that memory? Well, with an incredible escalating scale of units. At the very base level, computers think purely in zeros and ones, which we call bits. Group 8 bits together and you get a byte. From there, it just keeps multiplying by 1024. Kilobytes become megabytes, which then become gigabytes, and that's likely what your smartphone's RAM is measured in. But check out how this scales up. We go to terabytes, petabytes, through exabytes and zettabytes, all the way up to the absolutely astronomical scale of a yottabyte. The sheer volume of digital information we are capable of measuring today is just staggering. Data, though, isn't just a static thing sitting in a vault. It's highly active. It has a specific life cycle within the system. First up is data capturing. That's gathering the info from different sources into a digital format. Second is data storage, saving it safely in files or databases, maybe on a hard drive or a solid-state drive, so it's there for later. And third is data retrieval, fetching that stored data as quickly as humanly or mechanically possible so the CPU can process it. Minimizing that retrieval time is literally the key to a fast computer. To ground this concept, think about data capturing out in the real world. When you're at the grocery store and the cashier uses a barcode scanner, that physical red laser is converting a printed, physical pattern directly into digital input. It's this instant, almost magical transition from the physical world right into the computer's memory cycle.
Okay, so we know how the anatomy works today, but how did we actually get here? Let's shift our narrative to our next chapter, the evolution of computing from mechanical to microchips.
If we trace this progression back, computing actually started almost 3,000 years ago with the abacus, which was a purely mechanical device. For centuries, progress was pretty much entirely mechanical. But look what happens in the 20th century. In 1937, Turing conceptualizes general programmability. By 1945, the massive ENIAC implements stored programs. In 1947, transistors step in to replace clunky, burning vacuum tubes. And by 1970, we are suddenly packing entire circuits onto tiny little silicon chips. In the span of just a few decades, we transitioned from moving wooden beads on a wire to pushing invisible electrons through microscopic silicon. And the absolute driving force behind that rapid explosion? The number 2. In 1965, Intel co-founder Gordon Moore made a famous prediction that became known as Moore's Law. He boldly predicted that the number of transistors you could cram onto a single microchip would double every 2 years, all while the cost would get cut in half. That exponential doubling is exactly why computers shrank from the size of entire rooms down to sleek devices that fit right in our pockets. But here is the crucial takeaway. A smaller, faster physical body means absolutely nothing without instructions. And that brings us to our final major concept. Hardware needs software, the mind behind the body.
Let's really drive home this fundamental dichotomy. Hardware is everything we've talked about so far that you can physically touch or see. The RAM, the CPU, the keyboard, the monitor. It is the muscle of the operation. But software is the invisible set of instructions and data that actually tells that hardware what to do. Without software, the most advanced, cutting-edge processor in the world is literally just a very expensive piece of sand. The hardware is the muscle, for sure, but the software is the mind giving the commands.
And that digital mind is highly organized. We broadly categorize software into a few distinct areas. The bedrock foundation is system software, like your operating system. Think Windows, Mac OS, or Linux. This software talks directly to the hardware and manages it. Sitting right on top of that is application software, things like your web browser, a word processor, or a photo editor. Applications provide specific functions for you, the end user, but they rely entirely on the system software to translate things to the hardware below. And of course, hovering around all of this, we have programming tools used to actually write these applications. Now, the way we share these minds with the world varies drastically based on licensing models. Some software is proprietary, meaning it's owned by a vendor, you buy it, and the underlying code is a closely guarded secret. Then you have FOSS, free and open source software. With this model, the source code is freely available out there to be used, shared, and even modified by anyone, allowing the whole world to collaborate. And finally, freeware, which is totally free for you to use, but the underlying source code remains hidden from view. So we've successfully covered the complete anatomy today, from the input logic of the physical hardware to the organizational structure of the software. But as we all know, technology never just stands still. So I want to leave you with this final provocative thought. As we move way beyond traditional desktops and smartphones, how will the Internet of Things, embedding smart, connected sensors into our everyday appliances, and the massive explosion of artificial intelligence shape the anatomy of our next computing devices? What does the blueprint look like tomorrow? Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I will see you in the next one.